I had mentioned that there's a number of different parts of this UPS that are of potential concern thermally when I increase the output capability of it. However, there's two items that are of most concern. We have the transistors, the FETs over here, and the inductor. The inductor itself, there's very little that I can do to improve that except put in a new one, which I'm definitely not going to do. So for the transformer, that is, I'm just going to increase airflow. Hopefully that will solve that problem. Same with all the cabling in here. If I just blow enough air over them, I think they'll stay cool. The transistors, on the other hand, there's definite reason to upgrade those. First, I want to make sure to upgrade them because I know that they're going to overheat if I don't. Secondly, it increases the efficiency very significantly of this unit under load, which is definitely a good thing. And third, increasing these transistors will increase the surge capability of this unit. I'll do some demonstration in a little bit on exactly what that means, but the idea here is that I want to be able to have about a 3,000 watt surge capability for starting motors and compressors and such with this. As this is designed today, it's for computer equipment. There really is very little surge necessary for that sort of thing, but I want to use this as a general purpose inverter, which means I can run computer equipment and electric motors off of. I want to be able to plug my refrigerator or air compressor into this and have it start up, and that's no small feat for an inverter. It's a very difficult load to start. It requires a very large surge current to get it going, but that's the goal for this. So for this one, I have two ways of measuring temperature. I have this infrared thermometer, which I cannot use on these FETs because this is a metallic surface and the emissivity is not correct. I can, however, use it on the transformer. I've had this unit plugged in for a couple of hours now, trying to let the temperature stabilize. I had mentioned earlier that it takes about 50 watts on idle, which is what it is right now. It's on idle, also charging the batteries a little bit, but primarily idle. And this transformer has heated up quite a bit just sitting here. 46 degrees Celsius right now. It's almost stabilized, almost too hot to touch. And that's the 50 watts of loss that I had mentioned earlier. 50 watts right now in this transformer, and it's raised the temperature from about 25 degrees Celsius in here to, we'll just say 50 maybe once it's all stabilized. So we've got 25 C rise from 50 watts of load, and that gives me an idea of how many watts of loss this transformer can take before we get up to this 180 Celsius limit. But that's for another time. I don't really tend to stress test this transformer yet because it'll take almost all of the capacity of those batteries to really heat this up all the way, and I'm not going to drain my batteries and spend 2 hours of my time doing that right now. However, these transistors will be a lot quicker job. I'll put a fan on them to keep them cool, but in terms of benchmarking them today, I'm just going to run a heavy load briefly with no airflow. Then I'll upgrade it and do the exact same test again and see what kind of improvement I made. So I can't use my infrared thermometer on this, so what I'm going to do instead is use this thermocouple. It's just a very, very cheap meter, but it works for this purpose. It's about 25 Celsius in here, as this thing says, and all I'm going to do is, this is plugged into the wall, but I know that these are safe to touch. So all I'm going to do is take this thermocouple, tape it right here in between these two transistors. There we go. And we can see here in the meter, if I put it somewhere that's visible, that they are about 40 degrees Celsius right now, just here on idle. A lot of the heat on those is due to the batteries. They're still under a light charge, which makes those FETs quite warm, but that's not of great importance right now. So they're starting at 40, and I'm going to take my stopwatch here, unplug it from the wall, turn on this heater that I'd used earlier. I'm just going to put this heater on 900 watts. and let this thing run off a battery for a while. And I want to see how quickly that these transistors warm up to a point where they're dangerous. Once they get dangerously hot, I'll shut it off and record how much time that took. So we'll probably go to 70 degrees Celsius, maybe 80. I don't want to go too close to the limit, but we'll see how that works. That's on medium. And I'm going to unplug it, get it started. And it is now running off of battery with the heater running. And this will be boring to watch, so I'm just going to turn the camera off and turn it back on when the test is about finished. It's been running for about 4.5 minutes now, and you can see that the temperature is rising. This is the output waveform of the inverter with the 900 watt load, and you can see it's still a nice sine wave, which is good. I wanted to check that with all the components nice and warm. The transistors are reaching 70 degrees, which is going to be my stopping point. And the transformer has only increased by a couple of degrees. So there's 5 minutes and it's 70. So I'm going to shut it off right there. So it took 5 minutes for them to reach 70 degrees. That'll be my benchmark for when I upgrade it. The next thing I want to do before I make any modifications is to test the efficiency of the stock inverter function of this unit. Efficiency is important for a couple different reasons. One is battery life. The other is because if it's not efficient, then it will be dissipating a lot of heat inside the unit, which will have to be managed, and that will limit the output capabilities of it. So I want to check that before I make any modifications. So to check the efficiency, I have a battery bank here, and I need to measure the input current and input voltage. For input current, I'm going to use a clamp on DC meter here. For the input voltage, I have this multimeter connected up to the input voltage. I don't have it directly connected to the battery bank over here because there could be a fairly significant amount of loss in all this cabling that I have, and I'm really not interested in checking the quality of my cabling at the moment. So I have the negative lead connected right here to the case and the positive right here to the heatsink. So that way I'll check only the efficiency of this unit, excluding any losses in these cables. For the output power, I have this heater to act as my load. I want a primarily DC load so I don't have to worry about any sort of harmonics or lead or lag phase on the current. So I want to use a resistive load for that. And for the current, once again I'm going to be using this meter. I don't have two meters, so I'll have to swap between the two. For voltage, I just have some multimeter leads jammed in the outlet in the back, reading out the output voltage right here. I'm going to measure the efficiency of it under no load. Well, not the efficiency, but I'm going to measure the power use under no load and at about 900 watts. I could go through and make a whole efficiency curve, but I'm really not that motivated today. So first thing to do is to turn it on. On APC units, it's kind of a trick to turn them on. If you just hit the power button, they don't actually turn on. You have to hold it in until it beeps and then quick let go. There we go. Now it's running off of battery power. Right now I have no load on it, but I want to see how much power it takes just at idle on its inverter function. So I'm going to take my meter here, zero it out, clamp it on the cable, and I have 1.6 amps of input current at a battery voltage of 26.1 volts. That's at no load. Now I'm going to turn this heater on to medium. That should be about 900 watts. I'll be checking that with these meters. So now we're on medium. The battery voltage is still dropping. I want to let that stabilize a little bit before I take a reading. Looks like it's pretty well stabilized. So my meter zeroed out. I'll clamp it back on the battery cable. And it is consuming 43.2 amps at a battery voltage of 24.05 volts. The output voltage is 119.5 about AC, and I'm going to use this clamp meter to figure out my output current. And to do that, I'm just going to clamp it around one of these wires that goes to the outlet back here. And it looks like I have 7.3 amps AC of output current. So now we just have to run some math and we can get the efficiencies here. After some very simple math, I have the results of this test. Under no load, it takes 1.6 amps out of the battery bank. That's with the battery bank at 26.1 volts, which yields 42 watts. That would be primarily dissipated in the transformer of the unit. The specification from American Power Conversion Company is 50 watts standby. So this matches up pretty well. 50 watts standby would be primarily losses in the inductor and the transformer in this unit, a little bit in the FETs, and then the remaining would be float charge for the battery, because they'll always consume a little bit of current just keeping the batteries charged up. So 50 watts minus the battery charge, because we're not charging batteries when it's running off of the batteries. 42 watts is very close to what you'd expect. Under a heavy load, my 900 watt heater actually ended up being 872 watts. But there was 1039 watts of input power if I take the amps and volts here of the input and multiply it together. So that yields 167 watts of losses, or an efficiency of 84%, which isn't too bad. I was expecting about 80%, so I'm pleased with that. But that does mean that I have 167 watts of losses that I need to deal with. 167 watts is a pretty good amount, so I'm definitely going to need some fan cooling on that. But first I'm going to make some other modifications to this and see how warm things still get after that. I've taken a look at the thermal performance of the transistors inside this UPS. I've also taken a look at the efficiency of this unit when it's running in inverter mode. And the third thing I want to do before I make changes is to measure the surge capability of this. If you go to a store and look at the less expensive inverters on the shelf, the ones that are advertised as modified Sinewave, you'll probably find that if it's a 1000 watt unit, for example, they'll say 2000 watts peak. If it's a 1500 watt unit, they'll say 3000 watts peak. That 200% convention is really a matter of specsmanship. It's typically not true, just to put it bluntly. The reason they do that is because they know people will go to the store and they'll buy the one that has a bigger number on the package. And they know they won't get called on it because everybody does it. So just something to be aware of with UPSs. If you go with the higher quality units, Xantrex, or I think they're no longer in business actually, but the good quality names, they'll actually have a true surge rating. But in any case, I want to measure the surge capability of this inverter. The reason that that's important is that there's many loads in a typical household that may not require a lot of watts to run. For example, a refrigerator may only take 200 watts to operate, but it may take a lot of watts to actually get started. A lot of amps actually to get started. Some loads are very difficult to get started. So I thought a little bit about how to present this portion of the video, and I couldn't really come up with a clear way to get my thought process across without going into a lot of detail on how electric motors work, what harmonic distortion does to loads. It goes back to the modified sine versus sine argument. And instead of boring everyone to death, if anybody actually makes it this far in my video, in this series, to get here and wants to know more about it. Maybe I'll make a video response someday, going through some of the details of exactly why I did it this way and really what a modified sine wave versus sine wave inverter is. There's a lot of misinformation on the internet, I've noticed. Some of it's just outright incorrect. Other bits of it is maybe half-truths, and it's just enough information to lead people down the wrong path. So it's a little disappointing to me that way that the right information isn't out there. But in any case, if you want to know more, ask, and maybe I'll respond, maybe I won't, I don't know. But continuing on here, the load that I'm going to use to measure the surge capability of this unit is this wonderful looking humidifier from the 1980s probably. Somebody was throwing this away, so I picked it up. Still seems to work fine. The reason I'm using this is a couple of reasons. One, I don't have the proper laboratory equipment to do this accurately. But secondly, this is one of the most difficult loads any typical household has for a power inverter to start. This is an older unit with a reciprocating style pump. Some of the new ones have scroll pumps. The reciprocating pump is perfect for this application because when the piston hits its compression stroke, if the motor inside doesn't have enough power to compress the refrigerant inside, it can't turn over and I get a locked rotor current measurement out of it. But this is probably the most difficult kind of load that a typical household will have. I have an air compressor in the garage that might be a little bit better, but I don't want to haul that inside, so I'm going to use this. So the first thing I want to do is, I should mention one more thing first. This is convenient in another way too. It has this dial that I can just turn on and off. And because this is true of pretty much any refrigeration device, especially the reciprocating style pumps. Most refrigerators today still use the reciprocating pumps. Your heat pumps and air conditioners for your house use a scroll style pump for the most part anymore. But one thing that's nice about it for this application is that once you start the pump, the pressure differentials inside the unit build, and if it gets shut off and restarted without letting those pressure differentials even out again, it's actually incapable of turning the pump over. It just doesn't have enough starting torque, the motor inside. So I can pretty easily get a locked rotor current draw measurement out of this unit, and it'll be much higher than what it operates at normally. So the first thing I want to do is get this all set up. I have the UPS plugged into the wall. Looks like my dehumidifier is plugged into the UPS, and I'm just going to flip on my meter here, flip that around one of these wires that goes out to the dehumidifier, and see what kind of current draw this thing actually takes. So it's operating off wall power right now. I'm on DC amps, no wonder it doesn't show up. Alright, so it takes about 6.5 amps when operating. So now what I'm going to do is shut off the unit, and I'm not going to wait for the pressure to equalize. I'm just going to turn it back on briefly, and my meter went up to 33 amps. So this particular dehumidifier takes 33 amps to start up. That's 33 amps at, let's check the voltage on that. I have my meter plugged right into the back of the UPS. I should note that none of the stuff in the UPS is actually in the circuit. I have an extension cord to the wall, which probably adds some loss. And it just runs through a little bit of circuitry right here. The transformer isn't involved, the transistors aren't involved when it's running off wall power. It's just very isolated here. So that was 33 amps of AC power going to the dehumidifier. And it looks like about 109 volts is what's what's actually getting sent to it. There's quite a bit of loss when you're pulling 30 amps. Even in the wiring in your house, it's typically 12 gauge wire. I have it plugged into a 20 amp outlet, that's 12 gauge wire. But that has to run all the way to my fuse box, that has to run all the way to the outside transformer, etc. So there's a lot of losses involved. I have an extension cord, that's where a lot of it comes in. But even at that 107, did I say, volts, it still takes 33 amps. That's when it's running off of the wall power. So, let's see, I already looked at this earlier before I started the camera, and that ends up being about 3,500 watts. Some people might point out that that may not be in phase. The amps and the volts may not be in phase, and that's true. This is probably has a lagging power factor, but details, so we'll just ignore that for now. So next I'm going to unplug my UPS from the wall. Now we are running off of battery power. So this UPS will not shut down even with a severe overload for about 2 seconds. That's how these are set up. So I'm going to do the same thing with the dehumidifier now. First I'll turn it on. And it does start this dehumidifier even in its stock configuration, which is kind of impressive. I didn't really expect that. But I'll shut it off. Let the pressure not equalize and turn it on briefly. And I get about 20 amps at 80 volts. So it is not able to supply as much power as the wall. That's really not a surprise, but if I take those numbers and do the math on those, 80 volts at 22 amps, I get about 1,760 watts. So that's the surge capability of this unit, somewhere around 1,700 watts. And the dehumidifier, when plugged into the wall, has a surge draw of 3,500 watts. And the reason that the battery is lower, when it's running off a battery, the draw is lower, is because the voltage sagged to 80 volts. So I'm going to make some upgrades to this and see if I can increase the surge capability of it so that I can run the dehumidifier or a refrigerator or my air compressor or any other sort of induction motor pump applications, which are usually the most difficult loads for an inverter to power. Also the most difficult loads for a generator set to power. If anybody's tried to run something like this off of a gen set, it can be difficult to get it started as well. But so I'll get to the modifications next, I think.